The question 46 says we're given a line in Cartesian form. Remember, we're given a line in Cartesian form like this, and we're given a plane in Cartesian form as well. Our job is to find the intersection between the two. At this stage, probably you will appreciate the advantages the Cartesian equation of the plane gives you, because I'm still planning to do another example where we won't be having the Cartesian equation of the plane, and you'll see how the arithmetic goes longer in that case. But in this case, it's all relatively easy. You just have to convert first we have to convert my Cartesian equation of the plane into the parametric equation. I even suggest here, you see the name for the parameter, t. If you remember our discussions of this topic, then you know this transition from a Cartesian equation into the vector equation is just a pure reshuffling of numbers. We have to just take these numbers present in these equations and just put them in the right positions. Here's what we do. Here's the xyz vector. Then in my line there will be the a vector, the position vector, whose component 3, -2, and 1. Here they are, 3, -2, and 1. And there will be a directional vector for which the components are chosen from the denominator here, -2, 3, and 1. -2, 3, and 1. Parameter here, you can choose any name for the parameter. T is a very conventional name. Well, I chose T. Now, if I want to find the intersection, what I will do is this. I will take the expression for x in terms of the right-hand side here. I will take the expression for y in terms of the right-hand side here. I will take the expression for z in terms of the right-hand side here, and I will plug them in this Cartesian equation of the plane. If I do that, there will be one equation in terms of one unknown, which is t. I solve that. That will be the intersection. Here we go. Here's the expression for x. 3, take double t. Here's the expression for y. -2 and 3 of t. And here's the expression for z, which is 1 plus t. All of these now go into the equation of the plane. Expression for x in here, expression for y in here, expression for z in here. Here it is. 2 times 3 take double t, that's the x substitution. -2 plus 3t, this is y substitution in here. And 3 times 1 plus t, this is z substitution. And here we go. We solve for t. Well, I solve here for t. I just combine everything here. So it's a -4t plus 3t, it's -1t, plus another 3t, it's plus 2t. That's why we have double t on the left-hand side. Free term here is 6. Take 2, it's 4. Plus 3, it's 7. And then 7 goes on the right-hand side. 23 takes 7, it is 16. Which gives you t equal 8 as a solution. Now, if the question is find the point of intersection, which is true in our case, the last step which we have to do, we have to take this t and put across the expressions for x, y, and z. And that will deliver the point of intersection. Yes, that will deliver the point of intersection. So in my case, it will be the point with components, the point of intersection. It's the point A with components. If t is 8, so 3 takes 16, it's -13. 24 take 2, it's 22. And 9 is the point of intersection. It is not always true that you will have a solution in the course of these steps. It may happen that sometimes you come up here either with the equation like 8 equal 8, so numerical on the left-hand side, numerical on the right-hand side, no t present. So you will come up with the trivial true numerical identity, in which case that will be a clear case for the conclusion that the line is entirely lying on my plane. Meaning that for every parameter t, you do have a solution. For every parameter t, you do have an intersection. Geometrically, the interpretation for this line is on the plane. In other cases, when you end up with the numerical identity which is not true, like 9 equal 10, which means that for none of the parameters t, you have the solution. And that's a clear case for the conclusion that your line does not intersect the plane. You may rush to conclude that the line parallel to the plane, which is not true in general. It is true in 3 dimensions. In 3 dimensions, when you have a plane and a line, if they do not intersect, the only choice for them to be parallel, but it's not true in higher dimensions.